So let's look at the following example in which we're going to use the ideal gas law to calculate the temperature of a gas system. So let's begin. A certain container can withstand a pressure difference of 1 atm before actually collapsing. Now, initially, the container is filled with an ideal gas at 20 degrees Celsius and at 2 atm. To what temperature can you cool the container before it actually collapses? So, let's begin by looking at our two diagrams. So, system number 2 before we cool it and system number 2 after we cool our container. So, we want to cool the container in such a way that our new temperature or our new pressure does not exceed by 1 atm. So we begin with a pressure of 2 atm and a temperature of 273 plus 20 or 293 kelvins. So we cool our container to a pressure of 2 atm minus 1 atm. So the new pressure P2 is 1 atm. And the temperature T2 is what we want to calculate. So let's begin by first noticing that two things remain constant. The number of molecules and therefore the number of moles as well as the volume remains constant. So, the number of moles of our gas and the volume of our container remains constant during the cooling process. So, let's apply the ideal gas law. The product of pressure and volume is equal to the product of the number of moles, the universal gas constant, and the temperature. Notice that the volume, the number of moles, and our gas constant are all constants. So let's bring our constants to the right side and everything else to the left side. So we have the following result. The ratio of pressure to the temperature is equal to nR divided by V. Now this entire ratio is a constant. So that means P divided by T is also constant. So the ratio of pressure to temperature in system 1 is equal to the ratio of pressure and temperature in system 2. And that's exactly where we get the following equation. P1 divided by T1 is equal to P2 divided by T2, where 1 is system 1 and 2 is system 2. So let's rearrange our equation and solve for our temperature 2. So this is what we want to calculate. So we bring this to the left side, everything else to the right side. So temperature at system 2 is equal to P2 times T1 divided by P1. So pressure of system 2 is 1 atm. So we plug in 1 atm. The temperature of system 1 in kelvins is 273 plus 20, so 293 Kelvin. Now our pressure of system 1 is given to be 2 atm. So we have 1 atm divided by 2 atm, so that's simply 0.5 multiplied by 293 kelvins, and that gives us 146.5 kelvins. So the final temperature of our system number 2 right before our container collapses is 146.5 kelvins, or equivalently negative 126.5 degrees Celsius.